What does it mean to approximate a function with a polynomial function? Again, in terms of derivatives, if the zeroth derivatives agree, the function and polynomial approximation pass through the same point at x equals a. Well, the zeroth derivative is the original function. It's not. It says don't take a derivative. It's the function you start out with. If the first derivatives agree, then the slopes agree. So that's going back to the idea of what I said right back here about matching the slope. And if the second derivatives agree, then the curvature, the concavity, will agree. And then if I match up more and more derivatives, then I'll get more and more characteristics, and my approximation will become better, better, better as I get farther away from that point A that I'm trying to expand it about. Okay, so the tangent line approximation near x equals a looks like this. It is y equals f of a plus f prime of a times x minus a. And that's really, let me write it over here real quick. Remember this, y minus y1 equals m times x minus x1. Well, that's what this is, because y1 is f of a. F prime of a, that is what we use for the slope. That's f prime of a. And of course, x minus x1, the x1 is actually going to be the value a. Because remember, I'm going to have the point that I'm going to match it up with. The point will have the coordinates a, f of a. So, we want the zeroth and first derivatives to match for the linear approximation. And we will match further derivatives with other polynomial approximations. So let's rewrite this in terms of derivatives. What I get is y is equal to, and perhaps I should say approximately equal to, the zeroth derivative evaluated at a plus the first derivative evaluated at a times x minus a. Now I'm going to make one quick adjustment here. I'm going to rewrite this quickly here as the zeroth derivative of a times x minus a to the 0 plus the first derivative at a times x minus a to the first power. Because x minus a to the 0, that's 1. But I wanted to write it in this form because I think we can start to see a pattern starting to develop here. And that should inspire us to what the quadratic approximation would be. Well, based on this idea, I should have a quadratic approximation look like f or y equals the zeroth derivative at a times x minus a to the 0 plus the first derivative at a times x minus a to the first plus the second derivative at a times x minus a squared. So that's what, that would be logically what the next derivative will be equal to, or the quadratic approximation would be equal to. Okay, so now what do I have? We have both functions agreeing at x equals a. The first derivatives agree, and we're saying the second derivatives agree. But you can see here I have this little note, or does it? Does the second derivative really agree? Well, let's start taking derivatives, because here's my approximation. Let's start taking derivatives and see what happens. Y prime will equal, remember, x minus a, this is just 1. So this is going to be 0, because I'm taking the derivative of a constant, plus the first derivative evaluated at a, plus twice the second derivative evaluated at a times x minus a. Now I'm going to evaluate this at x equals a. When I do, this term, x minus a, goes to 0, so all of this term right here will go away. That would be 0. So the first derivative is nothing more than the first derivative evaluated by a. That's it. So that matches. That's great. So now let's take the second derivative, see how well that matches. F double prime, I'm still going to have this 0, plus f prime of a is a constant, so that will be 0 when I take the derivative. Plus, I'm going to have 2 times the second derivative evaluated at a. So this does not match. To make it match, I need to divide this by 2, so that these 2's will cancel out. which means this needed to be divided by 2, and way back up here, I needed to divide the whole thing by 2. Well, I'm going to rewrite this here just quickly. I'm going to suggest this form. How about y equals the 0th derivative evaluated at a times x minus a to the 0 divided by 0 factorial plus the first derivative evaluated at a times x minus a raised to the first over 1 factorial plus the second derivative evaluated at a times x minus a squared divided by 2 factorial. Because you see, when I start taking these derivatives, these exponents are going to start coming out, and they'll cancel with the factorial. So let's see if that will actually work if I go beyond this and end up with like a third degree, fourth degree, fifth degree, whatever polynomial approximation. See how well that's actually going to work. Okay, so what will the quadratic approximation actually look like? Well, I just did that. F of x will be approximately equal to the first derivative evaluated, the 0th derivative evaluated at a plus the first derivative evaluated at a times x minus a plus the second derivative evaluated at a times x minus a squared divided by 2. I'm going to write the factorial back in there, but 2 factorial is 2. And I didn't write it here, but I could have wrote 1 factorial and 0 factorial. By the way, if you didn't, in case you didn't know, as a reminder, 0 factorial is not 0. 0 factorial is 1. So, what is the quadratic approximation of sine x about pi of x equals pi over 2? Well, let's see. First thing I need is d dx of sine x, which is cosine of x, evaluated at pi over 2, which equals 0. Now I need d dx of cosine of x, which is negative sine x, evaluated at pi over 2, which is a negative 1. So this is my first and second derivatives. So my approximation should look like, I need the 0th derivative. I'll just write this evaluated at a equals sine of pi over 2, which equals 1. So my quadratic approximation will be sine of x is approximately equal to, see this 0th derivative, that's going to be 1, plus the first derivative, which is 0, times x minus a squared, to the first, plus this negative 1, so let's just make that a negative right away, minus 1 times x minus a squared over 2 factorial. Well, obviously, this is just 0. So sine of x is approximately 1 minus x minus a squared over 2 factorial. So that is my quadratic approximation for sine x about pi over 2. Well, almost. I need to add to this, what this is actually, I'm sorry, I kind of messed this a little bit. A is pi over 2, so this could be x minus pi over 2 squared over 2 factorial. There is my quadratic approximation for sine of x. All right, let's take this a little bit further. And what if we use a third degree polynomial? Well, let's see here. The second degree polynomial was, let's see, we had d dx of sine x. Now I'm going to write this differently. Let's write it this way. The 0th derivative there we go. The 0th derivative at a, and a, of course, is pi over 2, is equal to sine of pi over 2, which equals 1. The first derivative at a equals cosine of pi over 2, which equals 0. The second derivative A equals negative sine of pi over 2, which equals negative 1. So the third derivative at A equals negative cosine of pi over 2, which is equal to 0. So the third degree polynomial won't add anything. The third degree polynomial is the second degree polynomial. Matter of fact, if you look at this, you can see from these repeated derivatives that all of the odd derivatives, first, third, so again the fifth, seventh, all those will be cosine, either positive or negative cosine of pi over 2. Of course, cosine of pi over 2 is 0. It doesn't matter if it's positive or negative cosine. So all those odd ones won't add anything to it. So the third degree polynomial is of no use. It's a second degree polynomial approximation plus 0, which doesn't do any good. So to do any good, I need to stay even. So let's go to the fourth degree polynomial. Well, the fourth degree, or fourth derivative, evaluated at A, is sine of pi over 2, which equals 1. So my fourth degree approximation will be sine of x is approximately equal to 1 minus x minus pi over 2 squared over 2 factorial plus x minus pi over 2 to the fourth over 4 factorial. So this is my approximation for sine about pi over 2. If this was about 0, then this would be x squared over 2 factorial, and then x to the fourth over 4 factorial, you know, that sort of a thing. Because I'm putting 0 in for pi over 2. And actually, you need to take a look at these derivatives, because these 1s and 0s will also change, because sine of 0 is going to be 0 to begin with. Okay, so taking this a little bit further now, what about the fifth degree polynomial approximation? Well, I know, again, the fifth degree is going to be no better than the fourth, because that's odd. So what I really need is to increase my approximation to make it even better, better, better. What I really need is to go to the sixth degree. So the fourth degree was sine, or the fourth derivative. Which equals 1. So the fifth derivative is going to be cosine of pi over 2, which is 0. The sixth derivative at A will be negative sine of pi over 2, which is negative 1. So now I'm going to have sine of x is approximately equal to 1 minus x minus pi over 2 squared over 2 factorial plus x minus pi over 2 to the fourth over 4 factorial minus x minus pi over 2 to the sixth over 6 factorial. Okay, let's switch gears here for just a minute, and what I'm going to do is go to Maple, and let's go ahead and plot some of these and see what we get. Okay, so first thing I want to do, let's zoom in here just a little bit so you can get a better look at what's going on. I am going to plot, and I'm going to do sine of x, so we can see what sine of x actually looks like. And then I'm going to do the polynomial approximation, which will be 1 minus x minus pi over 2, and that was squared over 2 factorial. And let's go ahead and do this from x equals 0 to, let's go up to 2 pi. And y equals, let's say, negative 1.1 to 1.1. That should give us a halfway decent picture. Okay, so if you look at this, let me make this a little bit bigger for you. If you look at this, sine of x is this red line right here. This green one is our quadratic, and you can see that it actually matches at pi over 2, like I said it should. And close to pi over 2, this is a really nice approximation. Now when I start getting beyond pi, or even start approaching pi, I start getting this huge gap. It gets bigger and bigger and bigger, so the approximation is not nearly as good. So let's go ahead and add on the fourth degree. So this would be x minus pi over 2 raised to the fourth, and that would be over 4 factorial. So let's see what happens when I plot that. Well, see what happened is I got a really much better approximation here, all the way up to pi, and then I start getting some separation. But you can see the general shape now is starting to match the shape of my original function, sine of x. There's sine, there's my approximation. So I'm going to go out one more now, which is going to be minus x minus pi over 2. This is going to be raised to the 6th. Oops. Do it right there. Divided by 6 factorial. And see, now I even have a better approximation. So let's go just one more, because we know what the next one's going to be, right? The 7th is going to be 0, so don't bother with it. But I'm getting this alternating negative, positive, negative, so I know the next one's going to be positive. So I do a positive x minus pi over 2 raised to the 8th. Oops. Over 8 factorial. See, now I'm even getting a better approximation, because before it was coming down, now it's curving back up. And what's happening is, as I increase the number of derivatives, if I go out to the 10th, then the 12th, then the 14th, and then so forth, I will get better and better and better approximations. And actually, in theory, if you think about this, if I expand this polynomial out to an infinitely long polynomial, then it should actually, if you think about it, it should actually fit sine perfectly everywhere if I actually go out that far. So anyway, that's the basic idea behind, we're going to come to Taylor and Maclaurin series, but we're talking about right now about the idea of using polynomial approximations, which we will develop into Taylor and Maclaurin series to approximate other functions.